Good afternoon, class. We're going to continue with our discussion of freezing point depression. And where we left off last class was discussing examples of how freezing point can change once you introduce a non-electrolyte solute. And today what we discussed was colligative properties once you start including electrolytes. And electrolytes are things that ionize in solution. Ionize in solution. So a non-electrolyte solute does not ionize. So an example of that would be something like sugar, where we have C6H12O6. And that is a solid that has all covalent bonds bounded together, and it stays in solution when you dissolve the solid and make it aqueous. If you had 1 mole of the sugar as the starting material, you have 1 mole as the product. An electrolyte is different in that it ionizes in solution. So if you had 1 mole of sodium chloride solid, when it's aqueous, sodium becomes a +1 ion, chlorine becomes chloride, which is a -1 ion, and you are left with 1 mole of each with a total of 2 moles of ions in solution. So the way that you determine the freezing point depression of a non-electrolyte solute and an electrolyte solute is very different. And when you have an electrolyte, you have to use a different equation, and that includes something called the Van Hoff factor. So our delta T sub F equation changes a little bit, and that is now equal to K sub F times M molality times I, the Van Hoff factor. The Van Hoff factor is unitless and is equal to moles of particles in solution divided by moles of solute. So let's look at a few examples of how to determine that. So if we had calcium chloride and we had 1 mole and we dissolved it in water, we would get calcium in the +2 ion aqueous and 2 equivalents of chloride aqueous. So the 2 chlorines that are attached to calcium are actually 1- chlorides, and they separate from the metal and dissolve into solution. So we are then left with 3 moles of ions, 1, 2, 3. We divide that by the number of moles of solute, and we are left with our value of I, 3, our Van Hoff factor. If we had 3 moles of magnesium sulfate, we could figure out what our Van Hoff factor is dissolving in water. So magnesium sulfate separates and forms a magnesium 2+ ion and sulfate 4- ion, 1-to-1. Sulfate, as we know from the Lewis structure, is a 2- ion, but magnesium is a group 2 element, so it, like calcium, will lose 2 electrons to become isoelectronic to a noble gas, giving it a very predictable ionic charge. So if we had 1 equivalent of magnesium sulfate, we would have 1 of each. So if we have 3 moles, we have a total of 6 ions in solution, because for every 1 mole of magnesium sulfate, we have 2 total moles of ions in solution. So it gives us a total of 6 moles of ions in solution divided by 3 moles of solute that's given to us, provides us a Van Hoff factor I of 2. Scandium is a group 3 metal, and that is 1 over from calcium. So if we had potassium forms +1, calcium forms +2, and scandium would then form a +3 ion. Scandium is a transition metal, and transition metals can have more than 1 possible oxidation state, but scandium, being that it's +3, is also electronic to argon, just like calcium 2 and potassium 1, so it's still relatively predictable. So we can predict that scandium trichloride would break up into a scandium 3+ and 3 equivalents of chloride, giving us a total of 4 equivalents of ions in solution. So we would have 4 moles of ions, 1 mole of solute, giving us a Van Hoff factor of 4. Now in example 14, we are going to use the Van Hoff factor to determine the new freezing point of a solution once we've introduced an electrolyte solute. So if we had 0.710 kilograms of sodium carbonate, an electrolyte, dissolved in 10 kilograms of water, what would be the new freezing point? Well, sodium carbonate, we would need its molecular weight, which is provided to us in the problem, but you could also get it from the periodic table. The freezing point constant for sodium carbonate is provided. You could get that from a table, 1.86 degrees Celsius per molal. So let's write our chemical equation, and we'll figure out what the Van Hoff factor is. So if we have sodium carbonate and we had 1 mole of that, that would result in a total of 3 moles of ions once it ionizes, 2 sodiums and 1 carbonate. So if we were to figure out So in order to figure out the Van Hoff factor, we need moles of sodium carbonate. So moles of sodium carbonate can be determined from the mass that's provided. So we take 0.71 kilograms, multiply by 1,000 grams per kilogram to get our units in grams, and then we can multiply by 1 over the molecular weight to get our units into moles. So kilograms cancel with kilograms, and then 1 mole is equal to 105.99 grams, and our grams of sodium carbonate cancel with our grams of sodium carbonate, giving us 6.7 moles of sodium carbonate. We can then figure out how many ions we have in solution. And that's going to be equal to our moles of solute, 6.7 moles of sodium carbonate, times our moles of ions, 3 for every 1 mole of sodium carbonate. So here we have our moles of solute and moles of solute, and they cancel with one another. And so we're left with just moles of ions. And so for 6.7 moles of our solute, we are left with 20.1 moles of ions, given that this is an electrolyte. We can then calculate our Van Hoff factor I by taking our moles of ions, 20.1, and divided by our moles of solute, 6.7, which is equal to 3. So with enough practice, determining the Van Hoff factor can be pretty straightforward. I did go the long way here, even though it does appear a little bit redundant, and that's just to give us a little bit of practice in figuring out what the Van Hoff factor is. But if you were to figure out that for every 1 mole of sodium carbonate, you're left with 3 moles of ions, that is that's a reasonable shortcut to take. So now we need to figure out the molality of our situation so that we can then calculate the change in freezing point. So molality is our moles of solute, which we've already calculated, 6.7 moles of sodium carbonate, divided by kilograms of solvent, which is 10.7 kilograms of H2O, which is equal to 0.67 molal. We can then calculate our change in freezing point by multiplying our provided freezing point constant for sodium carbonate, which is 1.86 degrees Celsius per molal times 0.67 molal times our unitless Van Hoff factor 3, which is equal to 3.74 degrees Celsius. So the freezing point of our solvent has changed by 3.74 degrees when we formed our solution. And given that this is a freezing point, that's going to lower our freezing point. So the freezing point of our solution is equal to the pure solvent freezing point minus our change in freezing point. Water freezes at 0, and you subtract the change, 3.74, gives us a new freezing point of the solution of 3.74 degrees Celsius. Next, we're going to move into our next topic, which is thermodynamics. And we're going to move through some of this pretty quickly because a lot of this should be review at this point. So energy basics. Thermodynamics is a part of a broad topic called thermodynamics, which is the study of the interconversion of heat and other kinds of energy. Thermodynamics is very important to chemistry and engineering and other disciplines. We teach a 300-level course entirely on thermodynamics in the chemistry department, and so does physics. Energy can be defined as the capacity to supply heat or to do work. Work is the process of causing matter to move against a force. Kinetic energy is energy associated with motion. And potential energy is energy associated with position, composition, or condition. So for example, if I was holding my pen, it has a certain potential energy given that it's fighting the gravity force provided by the Earth. Now, if I start moving the pen up and down, I am creating a process of matter moving against a force. So moving my pen is work, although holding it in place gives it potential energy. Let's consider how heat energy is going to be useful for us. So let's look at the combustion of propane. If we have propane, C3H8, reacting with gaseous oxygen to form carbon dioxide and liquid water, we first need to balance this equation. So we have C3 on the left and just carbon on the right. So if we have 3 carbons, we can multiply carbon dioxide by 3 to balance the carbons. On the left side of the reaction, on the reactant side, we have 8 hydrogens. On the product side, we have 2, so we can multiply water by 4 to balance the hydrogens. And then we are left with 10 oxygens, 6 from carbon dioxide and 4 from water. So we can take 5 equivalents of dioxygen to balance out the reaction. So now we have propane, 5 oxygens, 3 carbon dioxides, and 4 waters. According to the law of conservation of energy, energy cannot be created or destroyed, but heat energy can be transferred. So the combustion of propane releases CO2 as gaseous molecules with a lot of kinetic energy. Now let's discuss the interconversion between thermal energy, temperature, and heat. So thermal energy is kinetic energy, which is abbreviated as Ke, associated with random motion of atoms and molecules. Temperature is the quantitative measure of hot and cold. But if something is hot, we can simply say that it has an increased or higher amount of kinetic energy, and if something is cold, it has a lower amount of kinetic energy. Heat, Q, is the transfer of thermal energy between two bodies at different temperatures. So a change that releases heat is exothermic, and heat can be shown as a product. A change that absorbs heat is endothermic, and heat is considered a reactant. And again, breaking bonds is endothermic, and forming bonds is exothermic. So if you have ever played around with hot glue, or super glue rather, it releases a lot of heat as you're forming many covalent bonds. And each one of those little covalent bonds, when it's formed, is releasing a little bit of heat, and overall it creates quite a heat release. So for an exothermic reaction, heat is a product. That is why back at the top, when we were discussing the combustion of propane, it releases heat, and so we can actually add heat on our our product side of the reaction. So moving on, we have a few more definitions. Energy units. A calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. The SI unit of heat, work, and energy is the joule. 4.184 joules is equal to 1 calorie, and 1 joule has units of kilogram meters squared per second squared, which you can write also as 1 kilogram meters squared times inverse seconds squared. And it's important at this point to point out that we have here a meter, which is different than our lowercase m molality, which we've been using already. So unfortunately, you'll just have to be able to know which m is which based on the context. Moving on, we can talk about heat capacity and specific heat. So the heat capacity of a body of matter is the quantity of heat Q it absorbs or releases when it experiences a temperature change delta T of 1 degree. And we can use the equation capital C is equal to Q, our heat, divided by a change in temperature. Heat capacity is what's called an extensive property, which means that it depends on the amount of matter. For example, a large frying pan will have a higher heat capacity than a smaller frying pan. More thermal energy is required to increase the temperature of the entire larger frying pan. So if you have a big frying pan versus a small one, and you start giving it energy, the larger frying pan is going to require more energy to heat up by 1 degree than the smaller one. Specific heat is the quantity of heat required to raise the temperature of 1 gram of the substance by 1 degree. So the only difference between specific heat and heat capacity is that we include mass in the equation, and we're sort of making it independent of the amount of matter. So here we have C is equal to Q divided by M times delta T. And here's actually our third M that we've seen today. This one is mass. So depending on the context, you might just have to figure out if it's molality, meters, or mass. For specific heat, we are dividing by mass, so we are making this an intensive property, which is independent of matter. So what you might say is that water has a specific heat of blank. Regardless of your situation, water is always going to have the specific heat value, making it independent of mass. But an ocean has a much higher heat capacity than a puddle. It requires a lot more energy to heat the ocean up by 1 degree than a puddle. We're going to do 2 quick examples of calculating specific heat. So first, we have 18,140 joules of thermal energy required to raise the temperature of 808 grams of iron by 50 degrees. We can take our specific heat equation. So small c, sub iron, is equal to 18,140 joules divided by 808 grams times 50 degrees. giving us a specific heat of 0.449 joules per gram Celsius. We can also calculate it for copper. So given that it requires 487 joules to raise 25 grams of copper from 25 degrees to 75 degrees, we can calculate delta T, which would be 50 degrees, and then we can solve for copper, which is 487 joules divided by 25 grams times 50 degrees Celsius, giving copper a specific heat of 0.39 joules per gram Celsius. Specific heat and its equation can be very useful to us in terms of solving for thermal energy Q, heat. So C is equal to Q over M times delta T. We can rearrange and get an equation in terms of Q. So Q is equal to mass times specific heat times delta T. In this next example, we can take an unknown metal that weighs a certain amount, 547 grams, and we can determine through experiments that it requires 4.94 kilojoules of heat to increase its temperature from 25.1 degrees to 96.2. And we can identify the metal. So Q is equal to MC delta T. Q given to us is 4,940 joules, which we just converted from kilojoules here. And that's equal to 547 grams mass times our specific heat C times our delta T, which is the difference of temperature, and that's 71.1 degrees Celsius. We can take this equation, solve for specific heat C to determine that it's 0.129. And we can compare that to a table of known values and identify that the unknown is in fact gold. And that's where we stop today.